Good morning, students. Last class we discussed about chemical kinetics. In that chapter, rate of reaction, factors affecting on rate of reaction. Last class we discussed about the 6 factors which affect the rate of reaction. Now the 7th factor, temperature effect on rate of reaction. Here, temperature effect. For every 10 degrees rise in temperature, rate of reaction is 2 to 3 times. Last class we discussed about this one. Next, so if we increase the temperature by 10 degrees, rate of reaction become 2 to 3 times. So rate of reaction is directly proportional to temperature. If we increase the temperature, rate of reaction increases. Here temperature coefficient. Temperature coefficient is represented with mu. Temperature coefficient is equal to K is the rate constant at T temperature plus 10 degrees centigrade by K is the rate constant at T temperature. So temperature coefficient mu is equal to Kt plus 10 degrees by Kt is called temperature coefficient. Now we will see effect of temperature on rate of reaction. If the temperature is T1 and T2, then rate constant K1 value, if the temperature T1 rate constant is K1, if temperature is T2 rate constant is T2, K2. Here we will discuss the effect of temperature on rate constant from the Arrhenius equation. Here this is the Arrhenius equation. Rate constant is directly proportional to exponential to the power of minus Ea by RT. This one we will get this equation from Arrhenius equation from the collision theory. Now just remember the formula K proportional to exponential to the power of minus Ea by RT. Here K is equal to, this one is proposed by Arrhenius. So K is equal to Arrhenius constant A exponential to the power of minus Ea by RT. Again from Arrhenius equation, K proportional to exponential to the power of minus Ea by RT. Ea is the activation energy, R is the constant, gas constant, T is the temperature, K is the rate constant. Now K is equal to, here proportionality constant A, Arrhenius constant, exponential to the power of minus Ea by RT. If we apply log base E both the side, here K, ln K is equal to, here A, ln A minus Ea by RT. If we apply the log both side, log base E. Now this is the formula. This is the relationship between log K, ln A minus Ea by RT. If you plot the graph in between ln K and 1 by T, ln K and 1 by T minus Ea by R is called slope, minus, so it is a negative slope, minus Ea by R. Again graph in between ln K versus 1 by T, ln K versus 1 by T minus Ea by RT is a slope, negative slope. Here this is the intercept value, here intercept value is ln A, this is the intercept value. This is about graph in between ln K and 1 by T. Now we will see the derivation, effect of temperature at two different temperature. What is the rate constant values? Here two different temperature. Here T1 temperature and T2 temperature. First one at T2 temperature. If it is T2 temperature, formula is, this is the formula. At T2 temperature, rate constant will influence rate of reaction. Rate constant depends on the temperature. At T2 temperature it becomes K2. So ln K2 is equal to ln A, this is the constant, Arrhenius constant, is it minus Ea by R 1 by T2, 1 by T2. At T2 temperature it becomes K2. At T1 temperature, here it becomes 1 by T1, Ea by R is constant. Next ln A is a constant, ln K1. If we take ln K2 minus K1, ln K2 minus K1, ln K2 minus K1 we can write log A minus log B, we can write log A by B. Now ln K2 minus ln K1 is log base C, K2 by K1, log K2 by K1. Now this value become ln K2 minus K1 become ln K2 by K1. K2 minus K1 is equal to ln K2 by K1, ln K2 by K1. Now ln K2 minus K1 is equal to this formula minus this formula, this equation minus this equation. So this one ln A minus Ea by R 1 by T2 K2 value, ln K2 value minus ln A minus EA by R 1 by T1, 1 by T1. Here ln K2 by K1 is equal to, here ln A plus ln A, this is minus ln A. Here minus EA by R 1 by T2. Here minus into minus plus EA by R 1 by T1. So we can write ln K2 by K1 is equal to EA by R plus EA by R is a common. Here this is a plus value, minus into minus plus 1 by T1, 1 by T1. This is a minus value, minus 1 by T2. If you multiply, say EA by R 1 by T1, EA by R 1 by T1 plus value, EA by R minus EA by R 1 by T2, minus EA by R 1 by T2. Next up, here log base E. Now we are taking log base 10, then ln log. If we take ln to log, we should multiply with 2.303. Then if we multiply here 2.303, we can take the 2.303 here also. Then it will become log K2 by K1 is equal to EA by 2.303 R. Here we can write T2 minus T1 by T1 T2, T2 minus T1 by T1 T2. This is the equation at two different temperature, rate constant value. When rate constant value we can calculate when activation energy value is given. Again, this is the effect of temperature at two different temperature. If the rate constant values are given, we can calculate the activation energy of the reaction. This is about effect of temperature on rate of reaction. Next topic is law of mass action. Here, one reaction is a general reaction. Small a, small b represent the number of moles. Capital A, capital B represent the reactant. So, small a, small b are number of moles, capital A, capital B are reactants. Reactants are react together and gives the product. Rate of reaction, last class we discussed. Rate of reaction depends on concentration of reactant. So, rate of reaction is proportional to concentration of reactant A to the power of A coefficient, concentration of B to the power of B. This square bracket represents the molar concentration. So, from this equation, rate of reaction or rate is proportional to concentration of A to the power of small a, concentration of B to the power of small b. At given temperature, rate of reaction is proportional to concentration of reactant raised to the power of their coefficients. Is called law of mass action. Again, at given temperature, rate of reaction is proportional to concentration of reactants raised to the power of their coefficients. Their coefficients are number of moles, small a and small b. This is called law of mass action. Here this law of mass action is theoretical value. If we take experimentally the same equation, if it is experimentally, that is called rate law. Now the formula is rate of reaction is proportional to concentration of reactant to the power of x, concentration of reactant B to the power of y. Here, from the same equation, here coefficients are A and B, but here coefficients are x and y. Why? Because this is the theoretical value, this is experimental value. Here we have taken number of moles of A number of moles A, B number of moles B. But experimentally, the reaction may depends on concentration of A, number of moles of A. It may depends on concentration of B, number of moles of B. Sometimes it may not depends on concentration of A, number of moles of A. So it may depends, it may not depends. So it is an experimental data. Now the definition here is at given temperature, experimentally rate of reaction is proportional to concentration of reactant A to the power of x, B to the power of y is called rate law. If it is theoretical, law of mass action. If it is experimental, this is called rate law, rate expression. So we should take always experimental data. So it represents the actual value, actual rate of reaction depends on. So from this equation, it is depends on concentration of A, concentration of B. Number of moles of A, number of moles of B. This is theoretically, but experimentally it may depends on concentration of A to the power of A, or it may not depend. So we should take x and y instead of A and B. So x and y are experimental values, A and B are theoretical values. A and B values are from the equation, X and Y values from experimental data. Now here the rate of reaction proportional to concentration of A, concentration of B to the power of X and Y. Here rate is equal to K. K is called rate constant. Rate constant. Concentration of A to the power of X, concentration of B to the power of Y. When concentration of A and concentration of B is 1, that rate of reaction is called rate constant. Rate of reaction is equal to rate constant. Now here X and Y are called X plus Y. We can take some of the powers of concentration terms. X plus Y is called order of reaction. That we will discuss in next topic, order of reaction. Now we will see units of this rate constant. Again, rate is equal to K into concentration A to the power of X, concentration of B to the power of Y. Here X and Y from experimental data, A and B from theoretical data. We should take always experimental data. Now units of rate constant. Units of rate constant. Rate constant is K, units of rate constant. Here reaction is rate is equal to K into A to the power of X, B to the power of Y. Concentration of A to the power of X, concentration of B to the power of Y. Here the same equation. We need to calculate the units for rate constant. K is equal to rate by concentration of A to the power of X, concentration of B to the power of Y. Now rate is nothing but decrease in concentration of reactant or increase in concentration of product. Rate is equal to dx by dt or dr by dt or dp by dt, concentration by time. So concentration by time, dx by dt, change in concentration by time, change in time. Rate is equal to concentration by time into 1 by, this is also concentration. Concentration of A to the power of X, concentration of B to the power of Y. So X plus Y we can take N. N is called order of reaction. N is called order of reaction. So we need to calculate first N. Then only we will get the rate constant units. Here concentration by time is constant. 1 by concentration to the power of, it may be 1, it may be 2, it may be 3. So rate constant units depends on N value. If we calculate the N value, we will get the rate constant units. So N is called order of reaction. So we need to calculate first the order of reaction. See here, this is order of reaction. Order of reaction is, what is order of reaction? X plus Y is called order of reaction. Is this from theoretical value or experimental value? This is from experimental value. So definition of order of reaction is sum of the powers of concentration terms involves in experimental rate equation. This is experimental rate equation. So sum of the powers of concentration terms, this value sum X plus Y, sum of the powers of concentration terms. This is the power value, these are the power values of concentration of A and concentration of B. So X plus Y is called order of reaction. Definition for order is sum of the powers of concentration terms involves in experimental rate equation. X plus Y is called order of reaction. It is a experimentally data. It is from experimental data. This order of reaction may be 0, may be fractional, may be a negative value also. Next, here this order will change with the temperature and pressure. With the temperature and pressure. And one more thing, here don't consider N value means N value starting from 1 to N. N may be 0 and fractional and negative values also. So N value is called order. It may be 0, it may be negative, it may be fractional values. So this order can change by changing the temperature and changing the pressure. Now next we will discuss zero order reaction, first order reaction which is there in your syllabus. Next zero order reaction. Zero order reaction. Zero order reaction is generally here one reaction is a reactants to product. Reactants to product. Rate of reaction is proportional to concentration of reactant to the power of 0. Rate of reaction is proportional to concentration of reactant to the power of 0. So rate of reaction proportional to concentration to the power of 0 means here order is 0. Sum of the powers of concentration terms involved in experimental rate equation is equal to 0. Then rate is equal to K into reactant to the power of 0. That means this rate of reaction independent of concentration of of reactant. Here, this is independent of concentration of reactant r to the power of 0. Then rate is equal to K. So rate of reaction is always constant. About this, you see the graph. Here, graph in between rate of reaction and concentration of reactant. Rate on y-axis, concentration of reactant on x-axis. By the concentration increases or decreases, there is no change in the rate. Rate is constant. About this one graph. Next, here rate is nothing but with respect to the reactant, decreasing concentration of reactant by change in time. Last class we discussed. Here rate of reaction is decreasing concentration of reactant, increasing concentration of product. Here decreasing concentration means with respect to the reactant minus sign, with respect to the product plus sign. So here minus dr by dt, dr reactant concentration by dt, change in time, change in concentration by change in time, minus sign represent decreasing concentration. If it is plus sign, increasing concentration is equal to, this is called rate, is equal to K. If we take next zero order reaction, zero order reaction is generally here reaction is a reactants to product, reactants to product. Rate of reaction is proportional to concentration of reactant to the power of 0. Rate of reaction is proportional to concentration of reactant to the power of 0. So rate of reaction proportional to concentration to the power of 0 means here order is 0. Sum of the powers of concentration terms involved in experimental rate equation is equal to 0. Then rate is equal to K into reactant to the power of 0. That means this rate of reaction independent of concentration of reactant. Here this is independent of concentration of reactant r to the power of 0. Then rate is equal to K. So rate of reaction is always constant. About this, you see the graph. Here, graph in between rate of reaction and concentration of reactant. Rate on y-axis, concentration of reactant on x-axis. By the concentration increases or decreases, there is no change in the rate. Rate is constant. About this one graph. Next, here rate is nothing but with respect to the reactant, decreasing concentration of reactant by change in time. Last class we discussed. Here rate of reaction is decreasing concentration of reactant, increasing concentration of product. Here decreasing concentration means with respect to the reactant minus sign, with respect to the product plus sign. So here minus dr by dt, dr reactant concentration by dt, change in time, change in concentration by change in time, minus sign represent decreasing concentration. If it is plus sign, increasing concentration is equal to, this is called rate, is equal to K. If we take dr here, dt comes here, so it becomes minus dr is equal to K into dt, minus dr is equal to K into dt. If we multiply with minus both sides, it becomes plus dr, here minus K dt. Again, if we take only dr, dt comes this side, then K into dt. If we multiply it with minus here, then minus into minus plus dr is equal to here minus K into dt. Next, integration of dr, integration of dx is equal to x, integration of dA is equal to a. Same way, integration of dr is equal to r, integration of dr reactant concentration is called r, is equal to, here this is a constant minus K as it is, integration of dt is t, integration of dx is equal to x, integration of dt is equal to t, plus integration constant I, here I is the integration constant. Then this is one equation. Reactant concentration minus K into T plus I. When the time is equal to 0, if the time is equal to 0, only reactants are present, products are 0. When the time is equal to 0, this part becomes 0. Then I is equal to R. Here R is called reactant concentration. When the time is 0, this R is equal to R naught, initial concentration. So is equal to, this is R naught. So R is when T is equal to 0, this value becomes 0. Then I is equal to R. That R is equal to R naught. I is equal to R. That R is equal to R naught. Then if we substitute R naught value here, then reactant concentration is equal to minus K into T. If we substitute the I value, that means R naught value here, this is the formula. R reactant concentration is equal to minus K into T plus R naught. Here 1 gram. See, reactant concentration versus time. By the time consumption, reactant concentration gradually decreases. That's why minus sign. Decreasing concentration, negative slope here, minus K. So by the time consumption, reactant concentration gradually decreases, negative slope. Same way, product concentration versus time. By the time consumption, product concentration gradually increases. Here gradually decreases, reactant concentration decreases, product concentration increases. Here decreases means negative slope, here increases means positive slope. So these are the graphs and the formula about the zero order reaction. Then again zero order reaction definition. Sum of the powers of concentration terms involves in experimental rate equation is equal to 0. So it is called zero order reaction. So rate is directly proportional to concentration of reactant to the power of 0, zero order reaction. Here reactant to the power of 0, then rate is equal to K, constant. Rate value is constant. This is rate value is constant independent of concentration. Next we will see units of zero order reaction. To calculate units, one formula is there. Here mole to the power of 1 minus n, liter to the power of n minus 1, second inverse. This is the formula to calculate units of zero order reaction, first order reaction, second order reaction. If we know the order, we can calculate the units of that order reaction. So rate constant of zero order reaction, first order reaction, second order reaction can be calculated by using this formula. Formula is mole to the power of 1 minus n, liter to the power of n minus 1, second inverse. Here n is called order of a reaction. Here it is zero order, so n value is 0. Mole to the power of 1 minus 0, value 1, mole. Liter to the power of 0 minus 1, answer is minus 1. Second inverse. So this is zero order rate constant units. Same units for rate of reaction also. What is rate of reaction? dx by dt, dr by dt. Concentration, moles per liter, mole per liter. Here time, second inverse. So zero order reaction constant units are same as rate of reaction units. Next, some examples of zero order reaction. Example, decomposition of ammonia is zero order reaction. If we write the theoretical rate of reaction is equal to reactant concentration, ammonia concentration to the power of 2. This is theoretically. If we see this value, we may think order is 2. But experimentally we should take. Then order is from rate law. Then experimentally this order is 0, zero order reaction. This one, decomposition of hydrogen iodide, it is also zero order reaction. Some photochemical reaction, the chemical reaction in the presence of light, photochemical reaction order is 0. And some enzyme catalytic reaction, the reaction which is catalyzed by enzyme. So these are the examples of zero order reaction. Again, this is the derivation of zero order reaction. Graphs, one is reactant concentration versus time, second one rate versus reactant concentration, third one product concentration versus time. Next one, units of zero order reaction, examples of zero order reaction. Next we will see first order reaction. First order reaction, we discussed about a zero order reaction. It's first order reaction. First order reaction definition is sum of the powers of concentration terms involves in experimental rate equation is equal to 1. So it is a first order reaction. General equation, reactant to the product. Rate of reaction is proportional to concentration of reactant to the power of 1. So it is a first order reaction. Concentration of reactant to the power of 0 means zero order. Here value is 1. So it is a first order reaction. So rate is proportional to concentration of reactant to the power of 1. Here rate with respect to the reactant. With respect to the reactant, decreasing concentration of reactant. With respect to the product, increasing concentration of product. So it is a minus sign. Minus dr by dt. Rate is equal to minus dr by dt is equal to proportionality constant K, reactant concentration to the power of 1. Next, here both the side multiplied with minus. So here minus into minus become plus. Here plus into minus, minus. Then the formula is minus dr by dt become dr by dt is equal to here minus r to the power of 1. Conservation of reactant to the power of 1. Next here dr by dt. If we take this r value here, reactant conservation here, dr by r is equal to dt comes here minus k into dt here, k into dt. Then integration both the side. Integration of dr by r is equal to ln r. Integration of dx by x is equal to ln x. Integration of dr by r is equal to ln r is equal to minus k. Integration of dx is equal to x. Here integration of dt is equal to t plus integration constant I. This is one formula. Formula is ln log base e. Reactant conservation is equal to minus k into t plus integration constant I. Here if t value is, if the time is 0, if the time is 0 means reaction not yet started, then this value becomes 0. Reaction not yet started means only reactants will be there. That is the initial conservation of reactant. Initial conservation of reactant is R naught. So if time is 0, this value becomes 0. I is equal to ln R naught. I is equal to ln R naught. If we substitute I value here, then become ln R is equal to reactant conservation is equal to minus k into t plus ln R naught. Ln R is equal to minus k into t plus ln R naught. This is about relationship between ln R and ln R naught. Here kt is equal to, this kt is equal to, kt comes this side plus kt is equal to R naught ln R naught. Here ln R on this side plus become minus. So kt is equal to ln R naught minus ln R. Kt is equal to ln log base e. Ln log x minus log y is equal to log x by y formula. Then kt is equal to ln log base e R naught by R. Next k is equal to t comes this side 1 by t ln R naught by R. This is log base e. When log base e is converted to log base 10 multiplied with 2.303, then the formula is k is equal to 2.303 by t log base e is converted into log base 10 log R naught by R. This is next step. Here k is rate constant for first order reaction, t is the time, log R naught is initial conservation, R is conservation at t time. Next here k is equal to 2.303 by t, this is common, log R naught is initial conservation, we can take initial conservation A also, then R is conservation at t time, so it is decreasing conservation A minus x, so we can write this formula or this formula for first order derivation. Now next graph in between ln R versus t, ln R versus t. ln R on y axis, time on x axis. Here minus k, so it is a negative slope. Intercept value is ln R naught. Ln R naught. This is the intercept value. Again, the plot in between ln R versus time. Ln R versus time minus k. So it is a slope, negative slope plus ln R naught. Intercept value is ln R naught. Next here, plot in between log R naught by R, log R naught by R versus time, log R naught by R versus time. Time here kt 2.303 here, kt by 2.303, kt by 2.303. Then the graph in between log R naught by R versus time, R naught by R versus time. Then here the slope value is k by 2.303, k by 2.303. Then the time increases, R naught, log R naught by R value also gradually increases. This is about graph in between ln R versus time and graph in between log R naught by R versus time. Next we will see units of first order reaction, and if the gaseous reactants are there, what is the formula about the first order reaction? From first order rate equation, we got this formula ln R is equal to minus kt plus ln R naught. after substituting the I value, integration constant value. This is the formula. ln R, reactant concentration, is equal to minus K into T time plus ln R naught, initial concentration. R naught is initial concentration, R is concentration at T time. Now we are going to derive equation when the time T1 time, T2 time are there. The difference between T1 time and T2 time, we are going to calculate the rate constant value, first order rate constant value. First, for this equation, at T1 time, if it is T1 time, concentration of reactant is R1, initial concentration is always constant R0. Again, we are going to calculate the rate constant value at T1 time and T2 time. At T1 time, here T become T1, then R become R1. Then initial concentration is as it is constant. Formula is ln R1 is equal to minus K T1 plus ln R0. This is equation 1 at T1 time. Next at T2 time, here R become R2, T become T2, initial concentration is constant, initial concentration is always 100%. Now equation 1 minus equation 2, that means T1 time minus T2 time. Then ln R1 minus ln R2, ln R1 minus ln R2 is equal to minus KT1 plus ln R0 minus KT1 plus ln R0 minus this formula minus KT2 plus ln R0. Here minus into minus, this value is plus, here minus into plus, this value become minus. So it is here plus ln R0, here minus into plus, minus ln R0, minus ln R0 plus ln R0 gets cancelled. Now we know ln x minus ln y, or log x minus log y, value is log x by y. Here ln R1 minus ln R2 is equal to ln R1 by R2 is equal to, here rest minus KT1 minus into minus plus KT2 minus KT1 plus KT2. Here common value is K. Then here ln R1 by R2, ln R1 by R2 is equal to, here common value is K into T2 minus T1. T2 is a plus value, T1 is a minus value. So T2 minus T1. Next, K is equal to, we are going to calculate the rate constant of first order reaction at two different times. Now K is equal to 1 by T2 minus T1. Here 1 by T2 minus T1, K is equal to this value from this side, 1 by T2 minus T1, ln R1 by R2. Reactant concentration at T1 time, reactant concentration at T2 time, T2 minus T1. Now here ln log base E, log base E is converted into log, then it is multiplied with 2.303, then K is equal to 2.303, T2 minus T1 log R1 by R2. R in some textbook they will give C1 by C2. Concentration 1 C1, concentration 2 C2. This is a T1 time, this is a T2 time. So K is equal to 2.303 T2 minus T1 log R1 by R2 or C1 by C2. Next, if the reactants are in gaseous phase, so first order rate constant, if the reaction takes place in gaseous phase, K is equal to 2.303 T2 minus T1 log, instead of concentration here pressure, initial pressure, next pressure PA at T time, one is at T1 time, one is at T2 time, then PI by PA. PA is equal to formula 2PI minus PT, initial time pressure minus pressure at T time. This is about if the reactants are in gaseous phase. Now final step, units of first order reaction. General formula we already discussed. What is the general formula? Mole to the power of 1 minus n, liter to the power of n minus 1, second inverse. N is the order. This is the first order reaction. So n value is 1. 1 minus 1, 0. Here 1 minus 1, 0. Second inverse. So first order rate constant units, second inverse. This is about zero order, first order rate equation derivation. Tomorrow in next class we will discuss about the half-life of a reaction, molecularity of a reaction. Thank you very much.